Anyway, my pleasure. Thank you, Radu. It's my pleasure to be here. Such a lovely city. And then the setup. See, our building, we are going to move into the building, a new building in our department. And when I come here, actually, I was admiring the space and then try to bring back some of the ideas for our new building, or at least for our department back in the States, of the setup. But anyway, so it's a great pleasure to be here. I want to talk about this subject here. Actually, there are three subtopics in the top, right? So the first one is about Heaviside composite optimization. And this is a class of problems, and I would say probably a novel class of problems that really have not received a lot of attention or any attention at all in the optimization community in terms of developing sort of guarantee algorithms of solid convergence theory as well as a good computation results. So that's the first class of problems. And the second class of problems, something that I'm sure many of you know about, is problems with complementarity constraints. And then these are very different classes of problems, right? And you actually see their formulations. And yet they can actually have a common feature. And in particular, my talk today is about how the common feature of these two classes of problems can be solved by a unified method, which is based on integer programming, right? So this is actually the two classes of problems actually are intersections of continuous and discrete optimization. Okay, so this is going to be a computational talk. There's very little theory. Okay, so if you're interested in the theory of these classes, particularly the first class of problems, which is the Heaviside composite optimization problems, there's two papers that actually talk about the basic underlying the theory, but the talk today is going to be tell you what the problems are, the model, the algorithm, and then a lot of computation results. Okay, so this is there's very little theory, but we do have two papers that talk about the basic theory of this class of Heaviside composite optimization problem. Okay. So introduction. So what are these problems? So Heaviside functions are step functions. They're discontinuous functions. Right? So you have the Heaviside function on the closed interval. Right? So I learned about these Heaviside functions when I was an undergraduate student, and we never encountered it much in optimization, at least not in the form that especially when you try to optimize functions of this kind. This is on the closed interval. It's basically nothing but the indicator function of the closed interval and the open interval. Right? So these are the Heaviside functions. And what we are interested is in the composition of these functions with another functions f. Right? So this is what I call the Heaviside composite functions. And then the function inside can be non-smooth, right? But they are continuous. Okay, so the discontinuity is due to the Heaviside functions, but the function inside here, they are continuous, but they may not be differentiable, right? So, and as a result, this kind of composite functions are discontinuous, right? They are depending, I mean, this one, because it's a closed interval, this one's upper semi, and this one is lower semi, right? And so it depends on whether you optimize, you maximize or minimize. For example, if you maximize this, right, then you're maximizing a lower semi-continuous functions, and that's not a very friendly problem, right? So they're discontinuous. And so therefore, in terms of developing algorithm, they definitely require approximations, right? Now, so why am I interested in this? Because there are actually a lot of problems, a lot of applications, that actually can be modeled using this kind of Heaviside composite functions. Okay. So the fundamental roles of this is in stochastic programming, for example, and used to model probability functions. You write probability of an event as the expectation of a indicator function, right? So that's the probability function, and then you get the indicator function of the either closed or open interval and compose it with another function. So plays a fundamental role. classification problems in machine learning and artificial intelligence and so on. It's like computational statistics. Classification functions basically are classification problems. Is that an object is classified. This can be even sort of multi-class classifications. And that, for example, for those of you who are familiar with the very classical Neyman-Pearson paradigms in classification, then you actually get into this kind of probability functions, and therefore you can use Heaviside function to model them. Okay? And then you can also have, one thing I want to mention here is that in computation, in statistics, you don't really see a lot of literature on constrained optimization, constraint classification problems. You don't see that a lot. Because I think that the statisticians probably don't really know how to solve constraint problems. Anyway, so in classification problems in particular, in the paradigm of Neyman-Pearson, very classical paradigm in classification, then you do get this kind of Heaviside functions, and also in structure sparsity, where you actually have logical conditions on the sparsity relationships among the different kinds of variable selections, and then you get into also this kind of Heaviside function. So this is very, very vague. I'm sure that you ask a lot of questions, so I'm going to hide all this because they are all in the literature. In fact, I've actually written a number of papers on this, but I'm going to put all this, hide all this under the rug, right? But just to mention to you that this kind of the Heaviside function actually plays a very fundamental role in the modeling of very different kinds of problems. Okay, so this talk is about two very different type problem classes. One has to do with the Heaviside functions, and the other, which is probably not so familiar to many of you, and the other class of problems is problems with complementarity constraints, which is by now a fairly kind of standard problem in optimization. So very different classes, but you can already see some kind of discrete disjunctive flavor in these two classes. And so when you think a little bit about these two problem classes, it will not surprise me that, it will not surprise you that they may be able to be treated by one common framework. And that framework is discrete optimization. And this is the second time that you see the word progressive. Terry, of course, used the word progressive for many years ago, even in disjunctive hedging, and today he used the progressive decoupling. And I'm going to use the term progressive integer programming. So what is that? So we all know integer programs, and you solve one integer program, right? But the way we're going to solve this is that we're going to solve a sequence of integer program subproblems. Now you say that I'm crazy, right? Integer programs are hard, so why do I want to solve a sequence of integer subproblems? The thing here is that you're going to solve the integer programming subproblems of progressively increasing sizes. So you start with problems of very small size, and you gradually increase the number of integer variables. And that actually turned out, very naive strategy, turns out to be very, very impressive. You get very impressive results. And that's where this progressive integer programming idea comes up. Okay, so there are very different classes of problems. This is actually after my talk, my neck will be, so I better stay here, okay? So very different classes of problems. The first one is this Heaviside discontinuous optimization problems because they involve the Heaviside functions. And I want to focus on the case of affine Heaviside composite optimization. So this is a affine Heaviside composite optimization. And this has applications in classification problems. And then you can also have domain constraints. And then economics is, well, in welfare economics, you get some kind of income inequality. And that also gives rise to the Heaviside. And so also so-called the layer variable selection under this kind of NO relations. So this is one class of problems, discontinuous. And the other class of problems is both old, very old, not too old, but of course definitely in the rather standard by now, but they're very hard. Okay? And this is a class of integral programs of linear complementarity constraints. And this actually can be applied to indefinite quadratic programs. And so we're going to apply this methodology to try to solve indefinite integral programs. And the hope is that we get better results. So one thing to keep in mind is that it's really difficult to try to improve a stationary solution by, let's say, any NLP solver applied to a quadratic program. Very difficult, right? So how can you try to improve a solution obtained by, let's say, the best NLP algorithms for solving an quadratic program? You need to use some sort of go outside the continuous domain. And this is where the progressive integral programming idea actually helps. And you'll see some results later. Okay, so let me tell you what this first class of problems is. Now you see this, right? And then the reason we call it affine is because you have constant coefficients here, okay? Constant coefficients. Now, you certainly can have functions here, but for this talk, I'm going to restrict to the case where the coefficients here are constants. Now you have this Heaviside composite. And I want to use maximize, okay, because one of my co-authors is an economist, and economists like to maximize. Engineers like to minimize, right? So I will maximize this. Now, what is difficult about this problem? A number of things. First of all, you can have discontinuity here. That's the first thing. And second thing, even because you have the closed interval here, I make a closed interval here, maximize, you would think that this would be upper semi-continuous, so that's nice. But then I'm not specifying the sign. Oh. I'm not telling you the sign of the coefficients, okay? So you have upper semi-continuous functions here, but if this is negative, then you can mess up your upper semi-continuity, and that makes it very hard, okay? So, but for today, I'm going to require that this coefficients here be positive, okay? My next paper, so if I'm invited back to the next One World Conference, I'll talk about a case where you actually have negative coefficients, okay? Negative coefficients here, and then when you have negative coefficients here, the problem becomes even harder, okay? But now, I would say just a week ago, I figured out how to deal with the case where these coefficients are actually negative. Very hard. Okay, so let's move on. The LBCC, something that I'm sure that you're all very familiar with, is you basically minimize a linear objective and subject to, let's say, I make it linear constraints here, and then you have this complementary slackness. The X variables is not involved in the complementarity, okay? So that's the LPCC. It includes in particular the special case of an indefinite quadratic program, okay? So this is the indefinite quadratic program. Q is symmetric, but it's not necessarily PSD, not necessarily PSD. And it's well known that dates back to 1960s, that optimal solution of this indefinite program is actually equivalent, it can be obtained, is equivalent to an LPCC where this is the set of KKT conditions of the problem, and then you simply minimize this objective. Okay, so if I have a methodology for solving this problem, I can apply it to this using this formulation, okay? But one needs to be careful. See, it is well known that a global solution of this is equivalent to a global solution of that. That's well known. What is not well known, and I'll be very happy if anyone can tell me that whether the local solutions of these two problems are actually equivalent. I don't know that. You can go one side, one direction, but not the other direction. Global solutions, totally equivalent. Local solutions, open. Okay, I don't know. Okay, if any one of you know about the equivalence of this in terms of local solution, let me know. Okay, I'll be very happy to. Okay, so that's the what I call the forward problem. Right? So this is just minimize a straightforward QP. Everyone knows that. And perhaps less than well known, but very, very useful in applications is the inverse case, which is a bilevel program, a special case of bilevel program. You can look at so this is the inverse quadratic program where you actually try to optimize the data given some, for example, historical vectors, C hat, D hat, and you're given a historical vector X hat, and you try to recover what CD is, and the X so that this is least deviate from the given tuple. Okay, so this is the kind of the inverse problem. Now, I also want to warn you that you see a lot of inverse problems in the literature. However, a lot of those problems are cheating, because when they talk about inverse problems, they don't have inequalities. Okay, so and that actually is because of this thing that actually make the inverse problems difficult. But in the literature, especially in the OR literature, the more applied literature, okay, when they talk about inverse problems, those are really easy problems. This is what makes the problem not easy. Okay, okay, so how do I deal with this? So I have two classes of problems. So this is for the affine problem. Okay, so let's go back. This is the one, right? This is the one here. And I can use a variable to substitute for this. Okay, you can use a variable substitute for this. And I call that Z. That's an integer, that's a binary variable, right? That's a binary variable over here, okay? And then I do the same thing for the Heaviside problem functions down in the constraints. So you have Heaviside here, Heaviside there, and they are replaced by binary variables, okay? And then as in the big M formulations of in integer programming, assume that there's a big M where you can actually restrict the, help you to formulate the Heaviside function. And the whole problem, this is the full mixed integer linear programming formulation for this affine Heaviside composite problem is to maximize this. You have binary variables, and then subject to the Heaviside functions being formulated in terms of a big M, where you have the integer variables here. So this is an integer program, right? So now you say that, oh, gee, I have a linear program. Why am I want to deal with this? Now, this formulation, again, this formulation is valid when the coefficients here are non-negative. When you have a negative coefficient, this integer programming formulation will not hold. Okay? So this is I emphasize the word full, okay? Because you do this for every Heaviside term. Okay, now, here's a problem. When this formulation actually is applied to some of the classification problems where you have a lot of data, a lot of Heaviside terms, the full integer programming formulation using the Gurobi solver actually sucks. Okay, you cannot go beyond maybe 100 or 200 variables. Very poor formulation. So because of that, I mean, we'll be very happy if we can use just an integer programming method to solve this. But we realize that we cannot, because it actually, after 100 or 200 variables, the problem basically, the solver just failed. You can't nothing. And so you cannot go even beyond, let's say 100, 200 integer variables, Heaviside terms. So we need to come up with alternative ideas. However, we know that the integer programming methods can solve this very well when you have let's say 100, 200 integer or Heaviside terms. So I want to take advantage of that. You are able to solve problems well with 100 or 200 integer variables or Heaviside terms. And so how do I take advantage of this success, okay, to solve problems, let's say, with 500 or 1,000 integer variables? And that's where the progressive idea comes in. So now, instead of the full, I have partial. And now what you see here is that, forget about this index set, but I do want to point out the index sets here depends on the current point. Okay, so you have a current point, And for that current point, I'm going to partition the index sets where some of this I'm going to fix integer variables, and then the others I'm not fixing the integer variables. So therefore, those becomes free. Yes? Oh, okay, very good question. Okay, it's feasible to this. Okay, and now you're probably going to ask me how I can get that. Okay, you're going to ask me how I can get that, right? Okay, yes and no. Yes, in the following sense, you can use a least residual approach. Okay, I'm sure you. So you can add a residual there, and then you minimize the residual, something like a penalty thing. Right? So he asked a very good question. I'm not always guaranteed, but then now you think about it in the case of quadratic program. Right? In the case of quadratic program, the complementary constraints are stationary solutions, and I can get stationary solutions. Right? But in general, the question is valid, very valid. How do I get a feasible thing? So in the case that we can not in general, then we use a least residual approach, minimize the least residual term. Okay, so I'm skipping that. Okay, so this is, you give a feasible thing, and you have 3 index sets, some of the variables are fixed, and so now what you have remains are the integer variables, a portion of the integer variables, okay? And then you're gradually going to increase the number of integer variables here. That's it. And now, how do you increase the number of integer variables? That, of course, is something. So now what you get is that you get for the LPCC is the same thing. Some of the variables, okay, so this is the full formulation for the LPCC, right? This is for the full integer formulation. And then you can also similarly define a partial. And the partial integer formulation is what I'm going to use. Okay. So the main idea is that the computational main step is to solve mixed integer subproblems by fixing many binary variables at either 0 or 1. And then you're going to solve so you have a small number of integer variables, and you're going to gradually increase the number, and that's where the progression is. You start with a large number of fixed variables, and you gradually, leaving very few binary variables left, and then you gradually increase the number of unfixed integer variables. At this point, okay, a lot of things are heuristics, okay? And so this is where some of the clever minds can help. But the idea, it seems very elementary. Gee, how come everyone can think of it? Right? Small numbers gradually increase the number of integer variables. Too simple, embarrassingly simple. All seem very elementary, very heuristic, but works. So, computation results. First of all, before I show you computation results, I want to summarize the findings. For problems whose globally optimal solution can be verified, okay, so you have the problem size not too big. You can actually verify, for example, by solving the full integer problems, that you actually know the global solutions. For problems whose global solutions you know, the PEEP, which is the method, progressive integer programming methods, obtains either the exact solution, or it comes very close. Comes very close of suboptimal solution, and this is the key. Significantly less time. Significantly. Okay? So that's one thing. The other thing is that for problems where integer programming methods do not work, don't give you much conclusion, the method can obtain, you can prove that the solution when the method actually stops is a locally optimal solution. Locally optimal. You can prove that. Integer programming, for example, if you stop, you really cannot say much. You get bounced, but then you cannot say much. But from a continuous optimization point of view, I actually can tell you that you actually get locally optimal solution to the continuous problem. Okay? So PEEP can obtain locally optimal solutions that otherwise cannot be obtained when you solve the full problem. Here's another thing that's more classical for indefinite QPs. Indefinite QPs and LPCCs, wow, I don't know how come there are so many S's. For LPCCs, PEEP is able to improve, and this is the point that I want to make. You give any solver, okay, you let any solver get you a stationary solution of a QP, and PIP can improve that solution. Okay, give you a better solution. And you see some idea, some results. Okay, so this is another sort of, I think that idea is very simple, but it actually goes beyond what has been sort of the bottleneck of solving indefinite problems for so many years. Okay, I don't want to solve the full IP. Okay, so I'm going to give you some results. I don't know how much time I have. Probably not too many. 2 minutes. Okay, so I'm going to give you maybe one set of results. You can either see the, okay, so this is, I'm going to read you this, okay? Read you all this thing. For this classification problems with only 300 variables, Gurobi performs pretty well. Okay, you can get the globally optimal solution. Okay, PIP's results are very comparable, but they're noticeably shorter times. I want to just point, there are 5 data sets. This is a full MIP, 40 seconds. And then the best, the PIP 40.4 means that I keep no more than 40% of the integer variables. No more than 40%. Okay, now you can see that the full IP is A5, this is 80, time here is 40, time there is 19, half the time. Okay, same thing here, 68, get exact global, 85, 85. Gurobi, and let's say full IP is 68, and PIP is 37. You can go on, and when you go to the, you have integer. Okay, so the integer, this is 1,000. Gurobi fails. Okay, so I want to show you this. Oh, this is start to choke. Okay, this is the case that the size when the method actually, Gurobi actually starts to okay, and then it actually slows down significantly, but then we continue to do well. Okay, so let's go on. Now, in this case, Gurobi, this is fails to find solution with, this is when you have tighter constraint. Don't ignore the word Gini. Has to, for those of you who know about the Gini coefficient, it actually comes into the constraint. Okay? And it fails to find for 1,000 integer, but then this is performs quite well in acceptable time. This is like 36,000, that's like 1 hour. This is like half an hour, and then you can see the solutions. 13.7, this is 14. This is maximized, by the way. Okay, so this problem is, this is welfare, so it's maximized. Okay, 15,000 is the same thing. Gurobi, 1 hour. This is the full MIP, 13.5, and ours is 14 something, maximized. And this is 1 hour, and then this is half an hour. But then you also see a lot of infeasible problems that Gurobi sort of stops. Okay, and then we get something like this. Okay, this is for the classification problems. There's another class that has to do with some kind of cost-sensitive healthcare problem. I'm going to skip that. I want to show you one. This is standard QP. Okay, now some of you, my professor, you probably, you're very, I think you are the one probably who created this term, right? So, yeah. So standard QP, that's a QP non-negative constraints, the simplex constraint. Okay? So, very small. Gurobi performs very well. Whenever Gurobi works like a charm. Nothing much can beat that. Okay, except maybe Tom, right? maybe you or your brother can beat Gurobi, right? But anyway, so for Gurobi performs well for standard QP. That's again indefinite quadratic objective. Okay, so I'm done. Okay, so it improves IP up. Okay, and then that's it. And then I want to go is 500 and then 500,000. Same thing, same conclusion. Okay, same conclusion. So I'm stopped. Okay.